Okay, so to this point in time, we have been working specifically with similar triangles. Although we did talk about it before, the definition of similar shapes is that they have the same angles and that their side lengths, corresponding side lengths, exist in a common ratio or common proportion. So again, similar figures, all angles are, sorry, not all angles. Let's write this as all corresponding angles are congruent and corresponding side lengths have the same proportion. I think with that written down, just so we're absolutely clear what's going on, I think that we'll be much happier. So because of this, we can extend this to any polygon. We can actually extend this to three-dimensional shapes as well, polyhedron, and the like. So that's what we're going to do today. So looking at these two rectangles right away, you can see, dealing with these, that we've got a situation where, yes, because the properties of a rectangle are that all of the angles are 90 degrees. So I can look at this and I can say for sure that we've got a situation where all of the angles are, all the corresponding angles are congruent. Now we just have to check to make sure that those sides are proportional as well, so that they exist in the same proportion, that is. So let's just check that real quick. So 6 is to 18, is that the same as 4 is to 12? Well, that's just a reduction thing. Can we reduce these two and have this work out? If I take a 6 out of the first one, I would end up with 1 over 3 by dividing by 6 on top and bottom. If I divide by 4 on this side, I get 1 over 3. So we can see that yes, these the sides are, they have a common ratio, and that common ratio is 1/3. So my constant proportionality, my K for this, is going to be 1/3. And again, we're going to call this constant of proportionality. And that's going to come in real handy moving forward, that we have this constant proportionality. Real quick, I just want to take a peek at something and deal with, I want to know what the relationship is between the area of the big triangle and the area, big rectangle, of the small rectangle. Real quick, just calculating this, area is always length times width. So this is 4 times 6, so this is 24. And we have units squared. And the other one here is area. It's again length times width. That's 12 times 18. I'm super lazy this morning. 12 times 18, 216. Well, looking at those two numbers, I don't necessarily see a clear relationship with them. Definitely, it's not 1/3, but there's something going on there. This smaller triangle, all of its proportions are 1/3 of the big one, okay? But the length is 1/3, and the width is 1/3. So in effect, what I have going on here, I could rewrite this in terms of the big one as the area of the small area is length times width, but I could replace the length as 1/3 of the big one, which is 12, times 1/3 of the big one again, which is 18. And I think what you're going to see when we do this, change that color real quick, cool, is now if I was to multiply this out, I could multiply 1/3 times 12 and I get 4, and that would check out. That is 1/3 times 12. I could do 1/3 times 18, and that would be 6, and that would work. But I'm going to do a trick here. I'm going to multiply my two 1/3s together. So 1/3 times 1/3, which is going to give me 1/9. And we already saw that 12 times 18 is 216. So if I just do that real quick, let's do 1/9 of 216. There's my 24. So what we're doing when we are trying to compare the area of similar figures, the area of similar figures is always going to be that k value squared times the area of 1 is going to be equal to the area of the second. That is a really important idea. We take that constant of proportionality and we square it because we're dealing with area. So by squaring it, we're able to manipulate or work with the area, and this will always work. So area, it's always this, the constant proportionality squared. Okay, that's a really powerful thing. It allows us to work all sorts of problems. Similarly, if we have volume, just think to yourself real quick. For length, we just multiply by the k value. For area, we multiply by the square of the k value. What are we going to do for volume? You got it. We're going to multiply by the cube of the square value. So of that common ratio. So for volume, we're always going to do the volume, the volume of one of the values times the k value cubed is going to equal the volume of the second. Okay? So we have these two prisms here. They're pentagonal prisms. The first one, we know the volume of A is going to be 15 centimeters cubed. We also know the side length of A is 3. Now, the big one that we want to find, the volume of B, well, that's what we're after, but we know that its side length is going to be 9. So we need to know what the k value is. We're saying that they're similar. So let's find our k value. So my k value is going to end up being, k is going to be 9/3. My k value in this case is 3. So to find the volume of the larger one, we're going to use this process above here, this exact same process, and we're going to do the volume of the first one, which is 15 times 3 cubed, will give us the volume of part B. And again, I'm going to just use my calculator. 15 times 3 cubed, which is 27. That would tell me that the volume of this pentagonal prism labeled B is 405 centimeters cubed. I think that's pretty easy, pretty straightforward, no big deal. Let's look at one more. Actually, that's the same idea, so I am not going to spend time doing that. I hope that's helpful. Good luck, everyone. And that just hit it. It didn't actually.